So my goal is to get this done in 10 minutes or less. Let's do it. So first you have this function. In terms of domain, we worry about square root of negative. So we say the radicand greater than or equal to 0, and we find that 2 must be greater than or equal to x squared. Well, how do I solve something like that? Well, you can think of graphing x squared, yes? And I want to know, where is this graph less than or equal to 2? Well, I know that x squared is going to equal to 2. They're going to be equal at plus or minus the square root of 2. So if you want to be less than 2, it's going to be inside this interval. So that is my domain. So as long as you stay in here, this will be good. Okay. Let's keep on going. So then the x-intercept is where y equals 0. I set this equal to 0. I get this or this. When you solve, don't forget when you take a square root, you get plus or minus. You get these intercepts. The y-intercept is where x equals 0. So when you put in 0, you get this. Vertical asymptotes are not applicable here. We do not have a denominator, and there's nothing that would let us know that is an issue. Then horizontal asymptote, we're worried about as x goes to infinity. Well, since x does not exist outside this, there is no long run. So you can't talk about a horizontal asymptote because it talks about end behavior. So there is no end behavior because there is no end. So increase, decrease, this is what we worry about. We write every time. Now we take a derivative and we get to here, right? Be careful when you take the derivative. Well, then we've got two terms. And we know in a minute when we do our work of asking where's the derivative equal to 0 undefined, we like fractions and factors. So since this is only one term, I use a well-chosen 1 to get the same denominator. And now I have a singular term where before I had 2, now I have one term. So then if I ask where the derivative is equal to 0, that's where the numerator is 0. So I solve and get plus or minus 1. Where it's undefined, a fraction, is where the denominator is equal to 0, and I get plus or minus the square root of 2. Notice those are going to be the endpoints of my interval, and they will not be able to be a local min or max. These are my only possibilities for local mins and maxes. So I partition, knowing that we already said that you must stay in here for this function, and those are my two values. So we make two cuts, essentially. We get these three intervals. I use the numerator and denominator to learn about the sign of f. That's why those go there. So when I fill out my charts, I find that these intervals are increasing and decreasing like so. And then we have a change of sign that lets us know we have a local max, and a change of sign that lets us know we have a local min, so max min. So if we go from decreasing to increasing, we have a local minimum. If we go increasing to decreasing, it's a local max. Concavity, take the second derivative. So here, low d high minus high d low over low squared. You just want to be careful, right? We do a little bit of simplification and get to here. Then from here to here, we need to factor out 2 minus x squared to the negative 1/2. Right? So anytime you have things to fraction and things to the negative version of that fraction floating around, or just in general, if you have a negative exponent floating around, you want to pull that one out to make your fraction a little nicer. So when you do, you ask yourself, this times what will get me the first term? Well, this times this, because this and this, we add exponents with like bases. That would give me what I want. And then we need one of these, so that's why that's there. Well, then this times what gives me stuff to the, what, negative 1/2? Well, since there's a 1 over here, times this, that's going to give us this 1. So then when we simplify this, well, we notice that now if we take this negative 1/2 and move it to the bottom, a positive, stuff to the positive 1/2 plus stuff to the positive 1 is where this stuff to the 3/2 comes from. But then all this simplifies to this, which then simplifies to this. And then on top we can factor out, and this is the form of our second derivative. So probably the hardest part was factoring out stuff to a negative exponent. So here, If this is our second derivative equal to 0, we get this. But notice we get plus or minus -3 also. That's outside of our interval, so we will not use it as part of our partition. Here, where the denominator equals 0, then what's up, people? 2 minus x squared. This stuff equals 0. Then you end up getting x squared is equal to 2. So you get plus or minus the square root of 2. But again, we know that those are endpoints because we've already done that. So in this case, you do your intervals, you find your concavity like so. Again, how do we know what to put? This is our numerator, this is our denominator, and then we have the factors of our numerator. And so that's all of our stuff, right? That's how we figure out what goes there. Since it changes sign, we do have an inflection point. So then putting our graph together, we draw our intercepts, and then we draw decreasing to increasing to decreasing. And then we use our second derivative information to show that this is concave up, concave down. So that must be an inflection point. Great work. 29, if this is y, the domain, notice that this is x to the 1/3. Is that x to the negative 1/3? I need to go back and double check that. That's x to the positive 1. Oh, x to the positive 1/3. It turns out that this is going to be, this is going to make sense everywhere. So you can put in everything. So x-intercept is where y equals 0. If we factor out an x to the positive 1/3, we get this. Set equal to 0, we get this. And then over here, we get plus or minus the 3 square root of 3. So we get this. So be careful that you know how we did this. Well, first, I had to pull out the x to the positive 1/3 because it's the smallest power. So then I say this times what gives me the first term. That's why it's x to the 2/3. And this times what gives me that term. Well, then this equal to 0, you end up getting x to the 2/3 is equal to 3. Well, that means at some point they want you to take the square root. Sorry, at some point they want you to take the cube root, and at some point they want you to square it. So to undo a cube root, we cube both sides to get this. And then to undo the squared, we take the square root of both sides to get this. That's where that came from. So make sure that you see that. Again, we already know 0, 0 is a point, so that's why we don't have to do it here. Then we take our derivative, and as often the case, that's where it's going to be difficult. So we get this is that, but then we're going to use a well-chosen one to get one term because we like fractions and factors when we're doing this sort of work with the derivative. Because if you ask where's the derivative 0, I say, hey, do you have a fraction? If so, just set the numerator equal to 0. Whereas the derivative undefined, I would say, well, do you have a fraction? If so, just set the denominator equal to 0. So we get all these values. When you chart it, looks like that. And notice we have some sign changes. So we have a local max and a local min. Concavity. I went back to the other version because it's easier. And when you take the derivative, you end up getting this. So we get, where's the numerator equal to 0? Well, never. Where's the denominator equal to 0? We get 0. So we really only have 1 point, and that turns out to be an inflection point, right? So putting it all together, it's going to look something like this. Now notice, oh, interesting. The second derivative changes sign there, right? The first derivative is undefined. Interesting. But we still do change concavity there. Let me look at my definition just to double check. Definition of inflection point. I was looking at the very strict definition. Give me a book. No. Inflection point. I wonder if we have to have the first derivative. So I'll double check in our book, but I'm going to say that is a inflection point. So great work. I'll do the next two here in a minute. Peace out.